Welcome back. All right, so linear regression. Typically, this will be covered in statistics when you're doing some kind of grade 12 data management course. Now, linear regression is typically a topic right after linear correlation. So I'm going to assume that you know linear correlation here. I did a video just before this, and I actually used this exact example there. So I'm going to use that. So these are the x and the y values. So we have two variables. We have a independent variable and a dependent variable. There's only really just 5 data samples in between them. That's all that I have. And then I put the mean there. So this is, again, just a sample. So the mean of 3 for x, and then the mean of 3.1 for y. And then obviously there's 5 values. So that's why n is equal to 5. And for that linear correlation, so again, so the link I'll put up above there. You should kind of watch that through, okay, if you wanted to know. So the main idea was that if you are given a data set, and typically it'll be much bigger than this, but it's much easier to explain on a smaller data set, and that's something that you should think about. Okay, when you're trying to grasp any concept, always try to understand it for something much smaller. So here, I have plotted these points, and the idea between kind of the whole linear concept of trying to match a data set to a linear line. So that line, y is equal to mx plus b. So your old line from elementary school, probably in grade 9 and 10 that you're working on, is that you have this scatter plot. Okay, in this case, we have a scatter plot between different points. So I have one point here, another point here, another one, another one, another one. And the idea was, can we find a line of best fit where that line, okay, will represent for us, okay, kind of that entire data set, as an approximation, as the best approximation we can with something which is linear. And the linear correlation concept was, and especially linear correlation, the coefficient, told us how strong that relationship was. And we know that it was basically between -1 and 1 that we have. When you're doing linear correlation, what you're actually trying to do, instead of trying to see how close analytically, okay, our data set is to a linear kind of a line of best fit, we actually wanted to be able to pull out. So we want to regress back from the data set and create our line in analytic form, y is equal to mx plus b. So we want to try to figure out what is the best m and the best b for the given data set. Now, when the correlation is strong, it's actually not hard to be able to do it by hand. So I drew this green line here, at least a green highlighted line. Okay, that's my line of best fit that I would have. But that's kind of guessing. And what linear regression does, it basically is trying to find a method which is not qualitative on a guessing side, but it is more analytical, and it tries to provide that slope and that b as best as it possibly can. Now, when we do that, I do want to talk about a little bit, okay, with regards to some terms. One term in particular, which is called residual. It's almost like calling it an error term. So if you think, let's imagine that the green is actually the line of best fit. I'm not saying that it is, but let's say that it is. So one thing that we like to define is this distance basically from the line, okay, and this is the vertical distance, straight to, okay, our data point. And this can happen, okay, between all of these. All right, so you can go from here to here, okay, and so on. And I can do it for all of these. So this one's very tiny, okay, and this one again is very tiny right here. Now, this distance, okay, is like our error that we have. And that is typically referred to as the residual. So that is the residual value. So now we have, so in this case, this one's very small. So let's call this, residual value number 1, which is between the, this data point, and the line of best fit. This would have been, let's say, residual value number 2, number 3, number 4, number 5. So you're going to have as many of those values. Now that is important to know. So I labeled it as an E, just kind of reminding us that it's an error. R I don't want to use because the linear correlation coefficient is designated by R. So I don't want to use R, so I just put E, which I like because it refers to an error in between. So now, if we know these residual values, right, and we want to try to find a line of best fit, if you would take 5, 10, 20 different people who would try to draw this line of best fit, it might be slightly different for all. In this case, the linear correlation coefficient is actually very strong, so this would have been easier to draw by hand, and the people who would be drawing it would be, maybe a little bit off, from each other. But now, what if I wanted to actually figure this thing out in total? So I have to define in some way what I am trying to minimize. What errors am I trying to minimize in between my line of best fit and the actual data points from my sample? And it turns out that we can do that. And typically what we do is we use, we try to minimize, the least squares method to find this M, so the actual slope itself, and the Y-intercept of our line of best fit. So this least squares, what is that? All right, so that's kind of the question that we want to be able to ask. Now, and I'll show you exactly what that is in just a moment. It turns out when you're using this least squares, it's not the only method. You might be minimizing something else. This is the one which typically is taught, for the linear regression. Regression, again, meaning going from the data set to a line of best fit. So it turns out when you do this method, we can find the slope in a very analytical way. Here is the equation for it. And sure, it's annoying because it's the summation, right, of the product between your X and Y values, from the data set. And then it's the summation of all the X values, summation of all the Y values, and then in the denominator you have them squared. And you might say, I don't even know what the heck this is and where it has come from. Now, when you're just learning this, which is this video, I'm trying just to explain to you what we're trying to do. No one will really show you exactly how this comes about. And I'm not interested in that, at least in this video. If someone ever asks me, maybe down the line, I might do a separate video. So here you kind of have to assume that this formula works and we can obtain our slope from here. We also have a formula which is going to give us the Y-intercept, which is the, so Y bar, which means basically the average of the Y values, all right, of the dependent variable, minus the M, which we just found up above there, times the average of the X values of the independent variable. So we actually have an analytical expression for these so that we can find this line of best fit, but this is assuming that we're doing these least squares. So what the heck is this least squares? Well, the least squares tries to do this. So I talked about the residual values, right? So you know what these are. So these are the residual values. And the least squares, so the least, it's trying to minimize. So if you're trying to think about, it's trying to minimize the summation between all the residual values if you square them, hence the squared, and least meaning what is the least number possible that I can get, all right? So that's what this is trying to minimize, trying to get the least number, but based on the assumption that your residual values, when you sum them up, are going to be equal to 0. That's what it does. Now, this is not an easy problem, but okay, if we're trying to minimize those least squares, those residual values, these ones right here, okay, if we're trying to minimize all of those, okay, meaning the square of all of those values that we had. So if you think about it for this example, it would have been, okay, so I have E1 squared plus E2 squared plus E3. So those are all the errors that I'm summing them up. Okay, whoops, I'm sorry. Okay, they're all squared. Okay, plus E5 squared. We're trying to minimize this entire value. All right, and under the assumption that all of them, when we sum them up, like so this is 3, this would be 4, okay, are equal to 0. That's the constraint under where we're trying to minimize that value. Now, if your data set, okay, is, let's say it's perfect correlation that we have, perfect linear correlation, then obviously the errors are all 0 already, so we can fit a line right there. But when it's strong or moderate or weak, okay, these values are going to be different. Okay, so that is the least squares. Now, from this entire thing, okay, you can actually come up with that. That's where it comes from. So that formula for M and B is actually pretty useful. So we can try to do this and we can find out exactly. So for this, at least this data set, what is, okay, my line of best fit under this assumption that I'm trying to minimize? And that's the one that you do for linear regression. It's the one that you study. All right. Now, I'm going to do it by hand so that you can see it, and then I'm going to show it up on Desmos, right? You can use a graphing calculator as well, but as you know, with all the videos that I've done and kind of how I teach, I love to do it through Desmos. It's a very powerful tool and super visual, okay? So I'll try to show you that as well. So let me take this data. So now I already have, okay, some of this right here that I need. So I'm going to take this. So let me copy this. Okay, let me bring it down, okay, right here. And now I'm going to kind of go over everything that I need here. So yes, I do need these, so I'm going to keep them. And then, you know, what else do I need? So if I go back here, I need the summation of the product between X and Y. All right, so that's the first thing that I'm going to do. So the summation of the product. So here, my product, okay, so XY, so I can extend this out, okay, and then do something like this, and then find that, and I can sum up the product. So 1 times 1 is 1, this is 4, this is 15, okay, and now let me go ahead and do that, and then I'm going to find the summation, okay, of the product between all of those. So that's one thing that I'll do, okay, except I'll do it in fast forward fashion. The other thing that I need, okay, is the summation of X and the summation of Y. So I can just sum up these values, okay, and then this value right here, so I can find out what those are. Again, I'll do that in fast forward fashion. And then that leaves me, okay, with the summation of X squared, all right, so I need that. And then this last one, I can just simply square the summation of that X. Okay, so I'll do that afterwards. So the X squared that I have, so I'm going to put another column here. So this is going to be X squared right there. Okay, and then I can do the summation of the X squared. So I'll fill up all of those. So let me be right back. All right, so welcome back. So I did that right there. So now I'm going to just substitute it into the formula. So I'm going to try to find out my m. So I'm going to do this kind of one by one. So notice, so this is 5. Okay, this is also 5. Okay, so the summation of x times y. So that's, so just right above there, that's 54.5. Then I have the multiplication of the x and the y summations. So that's 15 times 15.5. Summation of the squared. So that's 55 right here. And then squaring of that, so that's going to be 15 right here. So that is my m. All right, and I can compute that out. So let me just do that quickly. So that is equal to 0.8. So that's my slope. And now for my y-intercept, I will take, so this right here, bring it down. Okay, now substitute all of those in. So that's 3.1 minus 0.8 times 3. So I can find out what that is. This is 3.1 minus 2.4, which is equal to, I guess, positive 0.7. So my line of best fit on the least squares kind of method for this linear regression becomes 0.8 x plus 0.7. And I'm done. So that is basically the best I could do under this particular minimization for the linear regression. Now that I can, this is a lot of work if you're doing it by hand. And nowadays, again, you either will be using a graphing calculator or some kind of a scientific calculator with a stats that allows you just to enter the data sets, and then it will, it will give you linear correlations. It will give you, your regression, so model in terms of this one, the linear regression model, okay, covariance and all of those. I just want to show you how to do that in Desmos because it's super neat. I love the way that Desmos does this. So I just want to show you how to do that. And there's 2 ways that you can do it. So let me pull up Desmos, and then we're going to be entering all this data in. All right, so here I am in Desmos. So I'm going to do it in 2 ways. All right, so the first way that you can do this, you can, if you add a plus here, you can put a table. And then this table, so I can put these values in. So 1, 1. So this is 2, 2. This is 3, 5. This is 4, 3. And 5, 4.5. Notice that it plots it for you as well. So you see that on the right hand side there. So there's the plot. So that's the table itself. And now here's the beautiful thing about this. When you set it up as a table, so notice there's an x1 and y1. So those are the variables that we have. In Desmos, you can literally say simply y, okay, so subscript 1. And by the way, subscript, okay, the way that you do it is, okay, you use, okay, you're inputting it, so y, and then you press this, okay, on your keyboard, and then if you press 1, so that will put a subscript like this, okay, that you'll see. So that's how I am doing it in here. Now, so next, most of the time when we try to plot, we say y1 equals and then whatever we're trying to plot. But now we're trying to approximate it. So we put a tilde. And then that tilde basically is telling Desmos to start approximating from y1. Okay, so y1 is my output. And then x1, but I want to approximate it as, okay, a slope. So m, okay, is my slope. X subscript 1, notice, plus b. So I want to know what is the best with the y-intercept. And it literally gives me, so within here, notice that it gives me, maybe let me get rid of this entire thing so you can see it. So it plots the line for me. So that's 1, which is amazing. Okay, so I wasn't too far off in my original one that I did by hand. But it actually gives us, okay, r squared, right? It gives us r. So, you know, we have our linear correlation. Notice it's pretty strong there. It gives us the parameters m and b. Notice 0.8 and 0.7, which is exactly what I got using it by hand, but of course it took a long time. And then notice it gives us residuals. So it remembers the residuals in between and it can plot them for you. So if I do this, this plots the residuals. So one thing about the residuals are always, okay, so they're positive if they are above your line, and they're negative if they're below the line. So the red dots that you see, and also on the table on the left hand side, you can see the residuals there, right? Negative 0.5, negative 0.3, so that means those points are below the line of best fit. Then it has 1.9, so that point is above, okay? And then the other ones are also negative. And then, you know, if you would sum them up, like if you sum it all up, you should see, okay, that basically what you're going to get is 0 out of those residuals because you're minimizing least squares, right? So that's one of the constraints, and indeed that's what you will get. So this is amazing that Desmos does it, and it does it so fast, you know, and you can find out exactly those values. Another way of doing exactly the same thing, you can create, okay, so instead of doing a table, I think a table is a little bit better, but you can create a list of your items. So 1, 2, 3, 4, 5. So let's say this is my first list. I'm gonna remove these, okay, so that they're not there. And then I have B equals, so those are my Y values, 1, 2, 5, 3, 4.5. Just please put them in the correct order. And now you can do the same thing. So you know how we did Y1 tilde? So now our Y is our B values. Tilde, this is our, with a slope we want to approximate from the list of A, and then we want to have a Y-intercept. And it will give us the same values. The only thing is when you do a list, it doesn't actually allow you to plot the residuals. So notice there's no button there for the residuals. While here, there was a nice button where we basically plotted it out. So that's what we had. Okay, but the lines are the same and everything that it gives you is the same. You can, of course, get E2, so it's stored. So in this, the residuals E subscript 2, so it has 5 elements that we have, and we can certainly plot it. So if we wanted to plot it, we could on our own. The only thing is now it's a list, so you can plot it against X for all of those values. So you can do something like this. Okay, if you would be putting this in there, you know, it would have been A, because those are at the values of X that you want, and then the residuals themselves, and now it plots this. So that's how you can do that. So this is amazing, and you can do it for anything. So this linear regression, finding this line, okay, is awesome on Desmos. Desmos, you know, huge thumbs up on this. All right. Thanks for watching this video, and we will see you in future ones. Bye, everybody.